Hello everyone, I'm Shahidul Haq Shahid and I'm from Breck University, Dhaka, Bangladesh. And I'm really excited to present my research work with all of you, which is titled as Tinea Skin Disease Network, TISKIDNet, detecting tinea skin diseases through leveraging lightweight and unbiased deep convolutional neural network. So, tinea infections are the most common fungal skin diseases, which is affecting millions of people globally every year. And these diseases are highly contagious and it can spread through direct and indirect contact and also by contaminated items. And severe cases of various fungal infections is more than 150 million globally every single year. And the most alarming fact is that the number of deaths, which is approximately 1.7 million every year, with the highest infection rate at non-Mediterranean Africa, but there is also a high rate of infections in different regions of Asia, Europe, North Africa, Latin America, Caribbean, and Oceania. So, in terms of the visual signs of tinea infections, we can see a clear difference between the white skin tones and black and brown skin tones. For example, tinea capitis, it occurs on the scalp, and for white skin tone people, it shows red circular patches. But for black or brown skin tone, the symptoms are barely noticeable, or there is some inflamed bald patches. For tinea corporis, which appears on the body, and for white skin tones, it shows reddish circular rashes, but for black and brown skin tones, it's darkened or hyperpigmented patches. For tinea pedis, which appears on the feet, in terms of white skin tone, it shows red and flaky patches, but for black or brown skin, it's darker scaling or whitish discoloration. For Tinea angrium, it appears on the nails, and for white skins, it yellowish brown nails. But for black or brown skin, it's generally brown or darkened nail discoloration. So our research motivation was mainly that tinea infections is a global burden with over 150 million severe fungal infections annually, approximately 1.7 million deaths every single year. And there is also some challenges in existing models, like their bias towards single skin tones, leading to inaccuracies for other skin tones. And high computational demands make them unsuitable for resource limited settings. So we feel there is a need for innovation in this area as there is a lack of lightweight, unbiased CNN models for global usability, and also it's critical for improving healthcare in underserved regions. So our research objective was to build a deep CNN that can detect tinea infections across diverse skin tones, which is designed with low computational resource requirements for easy deployment in low resource environments. And we are aiming towards achieving high detection accuracy for tinea infections with a focus on minimizing bias across skin tones. And we want to ensure the model's suitability for practical use, including mobile or edge device deployment. So in this research, our key contributions are inclusive dataset. One is inclusive dataset, which we have developed an image dataset for 4 tinea infections, in which includes diverse skin tones, namely white, brown, and black. And we have also verified those images by dermatologists for equal representation and variety of the data. And we have also proposed a deep CNN architecture, which is lightweight, unbiased, and capable of detecting 4 common tinea infections. and it is optimized for real world deployment, especially in resource constrained settings. And further, we have conducted reliability tests across different skin tones, which demonstrate unbiased performance and high accuracy. A detailed comparison is also shown with the state-of-the-art CNN models, which highlights the superiority of our proposed CNN architecture. So this is the research methodology of our whole research. Here we can see all the processes that we have conducted throughout the research, initiated with a data collection of white, black, and brown people. Then we merged all the data and build a final raw image data set. After that, we have splitted the dataset into training, validation, and testing with a ratio of 70 to 20 to 10. And after that, we have used data pre-processing and augmented our training dataset by using different features like width shift, horizontal flip, height shift, and sharing. After that, we explored different deep learning CNN architecture and found out that our proposed CNN architecture, TiSkidNet, is superior to all other models. So our data collection was mainly we collected our data for black and brown skin tone images from Nigat et al., who have also worked on teenage skin diseases. And about white skin tone images, we have collected it from different internet sources and Google images. And here, as we are working with human skin diseases, we also received an approval of the Institutional Review Board IRB. We wanted to ensure that our model is not biased towards any features or any symptoms of the diseases. So we have ensured that it covers every type of symptoms for each classes. For example, here we can see different symptoms for tinea capitis. So for tinea capitis can have uneven scaly patches or severely infected scalp, or it can have barely noticeable patches or circular red patches. So we ensured that all these symptoms are in our dataset for each classes. And we have also consulted with a dermatologist to ensure that all these things are included in our dataset for each classes. So here is our dataset, which is consist of a total of 1023 raw images with white skin tone images of 655 and black and brown skin tone images of 368. And then we split our data set into train, validation, and test with a ratio of 70 to 20 to 10%. So this is the table of our augmented training data set. So we augmented our training data set and the number of white skin tone images and the number of black and brown skin tone images after augmentation are similar. So we have used 20 augmented white skin tone images, sorry, 200 white skin tone images and 200 black and brown skin tone images, and then combine with our raw images. So here we have ensured a balance between all the classes, the number of images between all the classes, and eventually the total number of our training data set images is 2,314. So this is the architecture of our proposed CNN, which is named as TiSkidNet. And here we have used four pair of convolutional 2D and max pooling 2D layer. And after that, we have used a flatten layer and followed by a dense layer. After that, we have used 30% of dropout in between those dense layers. And about the hyperparameters of our model, we have a input image size of 48 into 48, 110 epochs, and batch size of 32. And we have used Adam optimizer with a learning rate of 0.001, eventually achieving a total parameter size of 0.39 million approximately. So this is the training and validation performance of our proposed CNN model, and we have compared it with different state-of-the-art models like VGG19, Inception V3, Inception ResNet V2, and MobileNet. So here we can see that our model has a better training and validation accuracy than those models, and also a less number of training loss and validation loss. And in addition, we can see that our model trains better with the augmented dataset and in comparison with the without augmentation. So this is the performance comparison with those models, and we can see a clear distinguish between our proposed CNN architecture with those models. In terms of precision, recall, and F1 score, our proposed CNN model performs much better than those state-of-the-art architectures. And about the parameter size of our model is 0.39 million, which is much less than all the other four models here. So these are the loss accuracy graph and confusion metrics of our proposed CNN architecture. Here, for training and validation loss graph, we can see a continuous decline. And training and validation accuracy graph, there is a continuous or gradual increase, and which suggests that our model is not overfitted and it can generalize the features well. The confusion metrics also support these things. So finally, we wanted to do a reliability test of our model uh, to find out that our model is performing well with different types of data. Like here, we have used 40 images for each classes, and these 40 images are unseen and they are completely new to the model. And uh, we can see the similarities of performance of white people's data and the black and brown people's data. The model is performing equally well for white people's images and the black and brown people's images. The accuracy, precision, and recall, all of them suggest a similarity between those two tests. So we can conclude by this reliability test that our model can perform equally well for white people's data and black and brown people's data. So here are the comparison of our model with the existing studies. So we can see that our proposed CNN architecture outperforms all of them, and it can detect four different Tinea classes. And with also, it can perform equally well for white, black, and brown skin tones. But all those other existing studies, they are mainly for only single skin tones. So our model is capable of mitigating those barriers. And about the accuracy, we can see that our model performs much better than all those existing studies. So to conclude, I want to say that we have successfully developed a lightweight, unbiased deep CNN model by achieving a 97% accuracy, which also ensures equal performance across diverse skin tones, and it outperforms existing models in accuracy and applicability. In terms of future work, we plan to enhance the dataset with more diverse images across facial skin tones and also develop a mobile application integrating the deep CNN model for real-time detection and patient guidance. And we want to collaborate with dermatologists for future improvements and validation and expand this research to include additional fungal skin diseases and diverse dataset. So these are the references of different aspects of our presentation. And yeah, thank you everyone.